So for today and for Thursday, I need you to continue to stay focused because we continue to work on important parts of this subject. So today we talk about stress and strain. And essentially, so far, the kind of problems that we have been learning how to do have been problems in which I either have a bar in axial loading or I have a shaft in torsion or I have a beam in bending. And in general, we have been dealing with what we call slender structures, that is, structures in which the cross-sectional dimensions is smaller than the length of the structure. And by applying equilibrium and compatibility and constitutive relationship, we have been able to get an idea of how to predict the behavior of the structure in terms of the deformation of the structure, the stresses inside the structure, how to make sure that the stresses do not exceed some design limits, and so on. In general, structures can be more complicated in shape. So for instance, I can have a structure like this weird thing over here, and the structure can just be not just a slender bar or beam or shaft, but something more complicated than that. So when you have a problem in which you have a structure like this, typically you need to predict the behavior of the structure based on what you do on the structure. So the things that you impose on the structures are the boundary conditions on the structure. And you can either fix the displacement of the structure at a certain spot. In this particular case, I set the displacement to be 0 over this whole part of the boundary of my structure. On some other parts of the structure, you may set the loading on that part of the structure. So for instance, here I have a pressure P applied to this face. I have a traction T applied to this other face. And I actually am also applying traction boundary conditions to other places. Like here, I'm applying 0 traction. So even that is a boundary condition. So this boundary condition on displacement, we call them the insertion boundary condition. The boundary condition on the load, we call them the natural boundary condition. But essentially, the idea is that for your structure, in general, you would know what are the boundary conditions on the surface of the structure. You may also have some body loads, like gravity. But in general, you have a problem in which you know a bunch of things about how the structure is constrained and how it is loaded, and you want to find the solution. So in general, you can think of the solution in terms of the whole displacement field of x, y, and z. So the solution for a problem like this may be to find where every single point in the structure ends up once the structure is loaded. Because from this quantity here, I can get what is the strain at every spot, x, y, and z. I can get what are the stresses if I know a constitutive relationship between stress and strain at x, y, and z. And then from stresses and from strain, you know that somehow by integrating, we're going to get forces, displacements, rotations, and so on, right? So we know how to do that for these kind of structures. But for these problems here, and they're called boundary value problems because you know what happens at the boundary of the structure, to find the solution is not that easy, okay? Sometimes the solution, by the way, I just put function of x, y, and z. You know that they may also be function of time. If the material is viscoelastic or even if the material is elastic, if my load is a function of time, my strain will be a function of time, my stresses will be a function of time, and so on. So in general, the solution to boundary value problems is something that sometimes is not even possible. Most of the time, it's not even possible to do it in closed forms. Most of the time, if you have a complicated structure, the only way to solve the problems is to use approximation or numerical methods. And we are learning how to do some approximate methods in a very simple way using energy methods. But there are extensions of that that apply to any kind of constitutive relationship, not just the elastic relationship that we're using now. So in general, to solve this kind of problems is complicated. But at least one basic level of understanding that we need to get in this course before you guys are free to go on as continue your education as engineers is to understand, what is the stress? So I said we're going to get the stresses and strain at every spot. So what is the stress at every spot in something like this? This is not something in axial loading. This is not something in torsion. If I say I want the stress and the strain at every spot, what does it mean? So we need to understand a little more about what is the state of stress and strain in a complicated structure, in any structure, at a point in the structure. So we know the stresses and strain. So stress and strain, they are defined at each point of the structure, right? At each point, there is going to be a stress and a strain. So what do we know so far about stress and strain? So far, we have encountered, so what do we know so far? So far, we know a bunch of things. We know that if I start with something that has, say that I start with a cube of material with side length L, and L. So I start with a cube of material, and the material is linear elastic. So one thing that we learned is that let's put coordinate axis here. I say that this is my x-axis, that this is my y-axis, and this, therefore, is my z-axis. So I have a cube of material like that. So one thing that we know is that if we load the material in uniaxial loading, so now I'm going to do uniaxial loading and say about the x-axis. So if I take this block and I load it along the x-axis, we know that, so what I do is I apply a normal stress, what we call sigma, along the x-axis. And you know that if I load with the stress sigma along the x-axis, along the same direction, I'm going to have an axial strain, a normal strain, what we call epsilon. So that this side here now is going to be L that multiplies 1 plus epsilon, right? Because if it had a side L, the elongation will be epsilon times L. So this whole length is going to be L 1 plus epsilon. We know all this. We also learned in our little discovery lab that if I load something in axial loading, it extends along the direction in which I load it, but also changes dimension in the transverse direction. So we learned that if I have an epsilon strain in the direction of loading, and I'm just doing uniaxial loading, so I only have one stress in that direction, I also have changes in these dimensions over here. I'm going to have an epsilon transverse. So this length here now going to be L1 plus epsilon transverse. There is a transverse strain that happens. Most of the materials, when you pull them along the axial direction, they get shorter in the transverse direction. So the epsilon transverse is, if the epsilon is positive, epsilon transverse is negative. And we know how these guys are related through the modulus of the material. So we know that the axial strain is equal to the stress that I apply divided by the modulus, if this is an elastic material. So far, and we're going to talk, I didn't say something very important. That is, what I'm going to talk about today is just an extension of the linear elastic constitutive relationships. I'm not going to talk about an extension of the elastic plastic constitutive relationship, which are a little more complicated. I'm not going to talk about the 3D extension of the viscoelastic constitutive relationship. So what we have learned so far, we are focusing now on just elastic response. And we know that for elastic response, the axial strain is related to the normal stress through the Young's modulus. And we are learning we learn in our discovery lab that the transverse strain is connected to the axial strain through a material property that is called the Poisson's ratio. And because most materials have contraction, if you have extension in the axial direction, then the way that you normally write this relationship is with a minus sign. in the relationship. And that means that for most material, you're going to have a Poisson ratio positive. And with a positive Poisson ratio, with a positive axial strain, you're going to have a negative transverse strain. So we learn all this. And all these things have to do with epsilon and epsilon transverse, which are what we call normal strain. Normal strain. And they are defined in terms of percent change in length along a material direction, along a material line. So what does it mean? It means if I take this material line over here that originally had length L, all material lines along the x direction, this material line here now has a length L1 plus epsilon. It has a percent change in length equal to epsilon. So this line here that also had length L now has a length L1 plus epsilon transverse. So epsilon transverse is the percent change in length of this material line, right? Along the material line direction. So how much each material line changes. The other thing that we did is we looked at a different kind of loading and deformation. So while this thing here has to do with normal stresses and normal strains, so this thing here has to do with the stress sigma, which is obtained by taking the normal force and dividing it by the cross-sectional area, right? The stress that has to do with this kind of deformation is a stress that comes from a force which is normal. So our force N, the axial force resultant, the normal force resultant is normal to the cross-section. I divide the normal force by the area. I get the normal stress sigma. And my strain, the elongation, is a percent change in length. So it's going to be how much the material gets longer along a certain direction divided by the original length in that direction. We also looked at a different kind of deformation, and that was shear deformation. So in shear, we said, what if instead of loading the material normal to the surface of the block, I load it in a direction which is parallel to the surface of the block, like that. So what if I load the material with a force parallel to the surface, and our force parallel to the surface, remember, was our shear force resultant. Out of that, I get a stress, which is a force per unit area parallel to the surface, and we call that our shear stress. So we have a shear stress tau, and we defined as gamma that change in angle, right? So we said in this case, so this is if I have normal, and this is if I have shear. So if I have shear, now the stress, instead of being the normal force divided by the area, my stress is now the shear force divided by the area. And my angle, gamma, if this whole top move by delta t, delta transverse, or delta s from delta shear, whatever notation you want, this angle here and the length was L, my gamma is equal to delta shear divided by the length, if it is a small angle, so that the gamma is the same as the angle gamma is the same as the tangent of the angle. So the shear thing, the shear strain gamma, I define it as the transverse, the transverse deflection divided by the original length. And in terms of what gamma measures, so gamma, the shear strain, measure the change in angle between material lines that were originally at 90 degrees. So if I consider this line here, that's a material line that goes along with the y direction, actually, and this line here, L, it's another material line. Material line means if I go there with the pen and I mark with the pen all those points along these lines, the line that I create is a material line. It's like a line that is attached to the specific material points, so that when the structure deforms, this material line becomes this material line here, and this material line becomes this material line here. And what happened is that these two material lines have changed the angle between them. And the change in angle between these material lines is the angle gamma, which is our measure for shear strain. Okay, so far when we have defined all these stresses and strain, I have not even put anything about the coordinate axis, right? So now, in order to move from this simple world in which I just think about normal stress and shear stress, normal strain and shear strain, and they don't talk to each other, I need to go one step further and start thinking about a little more complex notation.